So let us continue our study of rational functions. So rational function again is a polynomial divided by a non-zero polynomial such as x plus 5 over x minus 1. And since the denominator is 0 at x equals 1, x equals 1 cannot be in the domain. So let's look at graph of this function here. So what I will do is this, that I'll go ahead and just enter this function. All right, so here I have this, then I got x minus 1, and let's look at a graph. All right, so here for the graph you can see that other than that x equals 1, the function is defined everywhere. Okay, and now you can see that there is a huge discontinuity at x equals 1. So let's look at a table of values to see what's going on near 1. So what I would do is this, that we can go ahead and let's go to say 0.9, because 0.9 is near 1. All right, and let's go say in the steps of 0.01. So we will have like 0.9, then 0.91, 0.92, then going to 1, and then towards the higher values. And let's see how the values look like. So at 0.9, the value is, quite small. And then as we approach 1 from the left side, what did I mean from the left side? That as we go from 0.9 to 1, we are approaching it from the left side. And what you notice in the table of values is that the value of the function, it just decreases, right? So at 0.99, it's negative 599. And if we just go further at 1, of course, it will give me an error, because the function is not defined here. And then on the right hand side, the moment you go to the right of 1, the values are huge, and then they are decreasing. All right, and they're coming towards 0. So what you note here is this, that let me just wait for it to stop. Okay, here. So what you notice is that as we approach 1 from the left, the function goes to negative infinity. And as we approach 1 from the right, the function runs to positive infinity. So in this case, what you do is you call, okay, x equals 1 a vertical asymptote of this function. Okay, all right, of of this function. Let's just call, I could write it as gx equals this ratio, but let's just go informally, function given by y equals this quantity, right? Okay, so now let's take up this quantity here. Okay, and I'm not going to go towards the graph here. Okay, and or let's take up a graph, it doesn't hurt. All right, okay, and so then and now I'm just going to graph it using this scientific notebook. You know how to graph it in your calculator. All right, so let me bring the graph into our viewing area. All right, just one more thing. So what you notice here is this, that is, remember the domain is the set of all real numbers except negative 1 and 2. And notice this, here we have a vertical asymptote at this part at x equals 1, and a vertical asymptote at x equals 2. All right, so, and if we look at this function here, where the domain is negative infinity to infinity, and again I'm just going to use this package to graph the function rather than, okay. So here what you notice, the the denominator is not equal to 0 at any point, and we notice that there is no vertical asymptote in this case. I mean, I can go ahead and enlarge the area. You can see there is no vertical asymptote in this case, right? Okay, so let's take up one more example. I'm just going to make up an example for you. Say I take the function given by, say, x squared minus 2x minus 3, all right, and there is another function, okay, say x squared, all right, plus 2x minus 15, all right. So in this case, if we factor the denominator, what we shall find is this, that is, the denominator factors as what? Negative 15, factors of 5 and negative 3. So sorry, yeah, I mean, you can use the factors 5 and negative 3 to get a 2 in the middle. Okay, so what happens? Domain here is the set of all numbers, okay, all reals. I'm just going to go a little informally, except who? Negative 5 and 3, all right. So let's go ahead and graph the function, all right. Okay, so we graphed it, and you can see this here. Oh, well, negative 5 is not included in the window, so let's try to include it here. So at negative 5, we do have a vertical asymptote, but we don't see any vertical asymptote at x equals 3. What the reason for that could be? Well, when I was factoring, I just did not notice that the numerator factors as x plus 2 and x minus 3. So what happens here is this, that of course x minus 3 is a factor in the denominator, which makes the function undefined at 3, right? But at the same time, what happens is x minus 3 is the factor in the numerator as well. So what happens in this case, that at x equals 3, you should have a whole rather than a vertical asymptote. Of course, this function cannot be continuous there. And since this grapher did not show us the whole, we can just go ahead and plot that whole ourselves. You may not be able to plot it in the calculator, but here we can. All right, so let's just put 3 here and 3 here. So what that would be, 5 over 8, and again I'm not, okay, so here. So there's a whole at x equals 3. So if we have to determine a vertical asymptote of a rational function, okay, so what would I do? Vertical asymptote of a rational function, okay, occur, okay, at the point, at the, yeah, let's just say at the points, okay, whose x coordinate, I'm just thinking out loud here, okay, x coordinate, okay, makes the denominator 0, okay, but the numerator is non-zero, or in simpler language, okay, in simpler language, what you have is that x minus, say, let's take alpha, okay, or rather x equals alpha, okay, a vertical line, okay, this is a vertical line, is a vertical asymptote, okay, of a rational function if if we have this x minus alpha is a factor of the denominator, okay, but not of the numerator, okay, but all right, of the numerator, okay. So now let's just go in the next video about discussion about another kind of asymptote, which is called horizontal asymptote. All right.